complex numbers, which is chapter 8 in the book. In this chapter, we're going to focus on complex numbers, which include imaginary numbers, as well as going forward, which is the focus on polar coordinates. And so we're going to spend most of the time in this chapter with polar coordinates. These imaginary numbers or complex numbers are a standalone section. And so to start with, the complex number is a number that has a real number in it and an imaginary number in it. So complex numbers are usually in the form of a plus bi, and a and b are actually real numbers. And I would be something called an imaginary number. So a complex number system contains both imaginary numbers and real numbers in it. It's the whole thing. So when you're looking at a Venn diagram for all the number sets, you're going to start with complex numbers, which is this a plus bi system. But within that a plus bi system, you're going to have imaginary numbers, and imaginary numbers would just be like a group here of AI numbers, like 2i or 3i or square root of 2i. And that's going to be one part of the complex number system. The other part of the complex number system, which is a very, I mean, they're all infinity. This is an infinite amount of numbers. This is an infinite amount of numbers. So the size of the shapes don't have any impact. The other one is going to be the real numbers system. And within the real numbers, you have two types of numbers sets. You're going to have a rational and irrational number set. And so we're going to make two circles there. And if we're talking about irrational, irrational means irrational. You cannot write a ratio. There's a reason why I said it like that. You may think that's funny, but really there's a purpose. No ratio can be written with integers. I-R-I-R-A-T-I-O. Oh, yeah, no ratio, irrational. So you can't make a ratio of integers, and that's what goes in that set. For example, square root of 2. You cannot put in as a ratio of integers. Or pi. Or e. Those are also, pi and e are called transcendental numbers, but they fit under irrational numbers because you can't form a ratio of integers. However, you can with this other one, which is rational numbers, and that has the word ratio in it. Well, within the rational numbers, and by the way, all this real number system, that's like the number line that you usually see in math classes, all the numbers on the number line. But the rational numbers are ones like integers, so you're going to have one big circle there, integers, and integers are where you have 0, plus or minus 1, plus or minus 2, etc. And you're also going to have whole numbers, and whole numbers are going to be where you have just 0, 1, 2, 3. And then you could even go further and call it counting numbers, which would be 1, 2, 3, 4, but you don't have to worry about that. That's the general way of organizing the number system. We are going to be focusing on complex numbers, which is the whole thing. It has real as well as imaginary in it. So the question now is what's an imaginary number? What is this I business all about? Well, I comes from, like, when you have a quadratic equation and you solve for it and you get a negative under the radical sign, you can't take the square root of a negative number, and therefore we create a system called imaginary numbers. You could be calling this system bologna sandwich system. It doesn't mean that you have to have that these things don't exist. It's imagined. It's not like you have to use your imagination to pull these things into place. So it's just that they called it imaginary numbers, right? Well, don't get confused. It's not like they're invisible. It's a system that is out there. We just have to work with a different system of numbers. And they called it imaginary numbers. Maybe because you have to use a little bit more of imagination. So if you have I is really the square root of -1. So for example, if you had the square root of -7, that's the same thing as the square root of -1 times times radical 7, which is the same exact thing as I times radical 7, or written in the correct form, radical 7 times I. So you can make them positive by taking the square root of 1 out and calling it I. All right, so that's where it comes from, and we've dealt with the quadratic formula and got negative numbers under there, and now we have a system that allows us to work with it. So what can we do with our I's? Well, you know that I is equal to radical -1, and you know I squared is equal to -1. Why? Because if you had I squared, it's the same thing as I times I, which is the same thing as -1 times -1. And you could rewrite that as square root of -1 squared. That's the same thing as -1 to the 1/2 power squared. To make a long story short, that becomes an exponent of 1, and you get -1. So I squared is really -1. Now, if we're to go back and look at I to the 3rd power, I to the 3rd power is the same thing as I times I squared. I know I squared is -1, so that becomes -I. -1 times I, -I. We're just going to leave it in terms of I. I to the 4th. I to the 4th is the same thing as I squared times I squared, which is just 1. Because it's -1 times -1, which is 1. Let's go ahead and go to I to the 5th. I to the 5th is the same thing as I squared times I to the 3rd. So that would be multiplying these two together, and you would end up getting I for them. Or, it's interesting enough, you could multiply these two together to get I, or you could multiply these two together to get I, because they both equal I to the 5th. Remember, you add those exponents when you're multiplying exponents, you add the powers, or other way around. When you're multiplying powers, you add the exponents. I to the 6th. I to the 6th. The easiest way to do this is to see what I to the 4th is, because that's equal to 1. Take out I to the 4th, you're left with I squared, which means that that's going to be equal to -1. I to the 7th. I to the 7th is the same thing as I to the 4th times I to the 3rd. I to the 3rd is -I, so that's just equal to -I. I to the eighth. I to the eighth, you can also think about this, because there's a lot of different ways of thinking about it, but I to the fourth all squared, right? Because it's I to the fourth times I to the fourth, that's equal to 1 squared, which is just 1. At this point, we see a pattern emerging from every 4 exponents of I. You're going to see that you're going from I to -1 to negative I to 1, and then it's going to repeat itself. And it's going to repeat itself again and again and again. In fact, every 4 exponents are going to repeat. So if I had, for example, I to the 100th power, I to the 100th power, I know that I to the 100th power is the same thing as I to the 4th 25 times, which is the same thing as 1. I to the 16th power, 1. I to the 24th power, 1. I to the 4 billion power, 1. Well, you can act really smart on saying what I to a certain power is equal to, because if the exponent is divisible by 4 evenly, you know it's equal to 1, because 1 to any power is equal to 1. Well, that's the easy case with 1. But if I go to, let's say, 17, I to the 17th power. I to the 17th power is I to the 16th times I. So it's just going to be 1 times I, which is just going to be I. Interesting enough, if I can figure out how many 4s come out of that exponent, I know that just that number, I to that number, is going to be 1. Then you're really concentrating on how many left over do I have? How many I's do I have left over? If you have 1 I left over, you're just left with I. If you have 2 left over, it's -1. If you have 3 left over, it's negative I. In fact, the leftover is the same idea as what? Remainder. Good. So we're looking at remainders when we're thinking about multiples of 4. This is going to be remainder 1, remainder 2, remainder 3, and the remainder of 0. Well, let's see. I to the 35th. I to the 35th. 4 goes into 35. 8 times with the remainder of 3. Remainder of 3 means this is going to be negative I, and I'm done. Fun. I to the 103. What's the multiple of 4 and 103? 100. And then how much left over do I have? 3, which means that's going to be negative I. In fact, what you could do is just divide by 4 and see what the remainder is. So if I took 4 into 103, I can see that's going to be a 25, and there's a remainder of 3. Now let me warn you, on your calculator, when you divide 4 into 25, it's not going to say remainder 3. It's going to say 25.75, and if you want to find out what that remainder is, you're going to have to take 0.75 and multiply it by 4 to get your remainder of 3. So that's a little bit weird when you use your calculator. It doesn't spit out that remainder, but it is hidden in there. Well, that's kind of fun. Let's go to the second idea. Number 1 on imaginary numbers. Imaginary or complex numbers have real and imaginary parts. This is an example that says if you have a real and imaginary part and it's equal to a real and imaginary part, Then the reals have to equal, and the reals of the imaginaries have to equal. In other words, these two, A and C, have to be equal to each other, so you can write an equation, A is equal to C. Whatever A and C is, you can set equal to each other and solve. The other one is this B has got to be equal to that D because that's the imaginary part of those complex numbers. They have to be equal to each other. Whatever they are, you can set them equal to each other and have an equation and then solve for what that is. And then adding them is as easy as combining like terms. That's all you have to remember. Treat I like it's a variable, like it's an X, and combine like terms. Simple. I'm just going to do 3 quick problems to show you that you can multiply complex numbers and you can divide complex numbers. So let's go ahead and multiply these. The whole thing on these imaginary numbers with these operations is that you want to treat I as an X and then just do the same thing as what you did before. So treating I as an X, you're just going to do the 4 multiplications and then simplify. And there's just one more step involved with these imaginary numbers. So this is just going to be, you're going to do distribution twice through. So it's going to be 6 minus 15i minus 8i plus 20i squared. And then it's going to be 6 minus 23i plus 20i squared. 20i squared is the same thing, remember, as 20 times negative 1. So it's really minus 20. I squared is negative 1. We saw that in the other slide, right? I squared is negative 1. So negative 1 times 20 is negative 20. And then I can see that my answer here is just going to be a negative 14 minus 23i when you combine the like terms. So it's just like foiling, but what you want to do is remember that I squared is negative 1 and then combine like terms. Let's go to the second one. Same idea. I'm going to do the distributive property twice. 9 plus 12i minus 12i minus 16i. The 12i's become 0, and now you're left with 9 minus, and then it's really 16 times negative 1, so that's just going to end up to being 25. Now, the only other idea is if you have something like this, where it's 5i divided by 2 minus 3i, and just like you can't have a radical in the bottom, in simplest form you can't have an I in the bottom. So we have to get rid of the I in the bottom, and the way to do that is just to remember a trick, and that is you want to multiply by like the conjugate of that denominator, which means you just have to change the sign in between the two terms. And if you do it on the top, you've got to do it on the bottom. So it becomes 2 plus 3i. 2 plus 3i on the top and the bottom. And when you do that, you end up with, let's see, 10i plus 15i squared over, the middle terms cancel. So I don't have to worry about that middle term, 4 minus 9i squared, which means 10i plus 15i squared, which really is the same thing as minus 15, because I squared is negative 1, minus 4 minus 9 times negative 1. All right, so that means that it's going to be, now in there's standard form in complex numbers. And the standard form is where you write the real number first, followed by the imaginary number. So really it should be negative 15 plus 10i over, and then this becomes 13. I can't simplify this anymore. If this were 15 on the bottom or 5, I could simplify it more, but that's as simple as I can get. Some books will furthermore break this down into two parts, focusing in on the numbers. So they may do something like this, because you have a real number and imaginary within it, and that's kind of hidden when you do it that way. They don't like to combine them. It gets spooky. Okay, so that's imaginary numbers, and tomorrow we're going to start with polar coordinates, which will be a system, and you're not going to want to mess tomorrow because that's going to be the basics of 3 or 4 days to follow.